Right. Uh, Welcome everyone to another session in the series Applications of Game Theory. So we have had two talks by Gaurav Atreya and Jack Bara before on aspects of game theory. And today we have Giacomo, who's going to talk about uh, who's going to talk about the much of his work that he's doing currently in his PhD at University of Catania. So this work was mainly based on what he presented in the 17th International Conference on Complex Networks, where he also won the Best Post Award. And he has Abhishek had informed that he also has multiple talks, which is accessible on his YouTube page. So be sure to check them out. So without any further ado, let's start the talk titled Endogenous Incentives Reshape the Stability of Cooperation. The stage is all yours.
Thank you. Thank you very much. Thank you, of course, for the invitation. I'm really grateful to Fishes Society and, of course, to my friend Abhishek for the invitation who made this contact possible. Probably I'm the first Italian to deliver a talk in this series, so I'm really happy about it. I hope that there will be many more people around the world to join this beautiful series that you're organizing. So today I will talk about cooperation. So this will be the main topic. And today's recipe will be to explain cooperation, starting from why it is an interesting question to study cooperation, then to introduce some aspects from evolutionary game theory and social dilemmas in general. And then later I will try to explain my recent work about endogenous feedback and chimera games. So I think that we can start from the beginning. So let me see if I can move. Yes, perfect. So the puzzle of cooperation. So why do individuals cooperate when selfish behavior can be individually advantageous? So we know that in general, in the real world, we see cooperation which is widespread. So even if it comes with a cost, because of course cooperating is costly, we see cooperation in many real world systems and real world scenarios. For example, we see animals grooming and collaborating to, for example, and sharing resources or collaborating for hunting and so on. We see microbial communities who have shared resources and they evolve cooperating with each other. And of course, we have many more examples also from the human side. For example, we have scientific communities where we can collaborate with each other, and we see also a high level of cooperation in this kind of systems. And one of the main example, my favorite one is about the First World War. And this example comes from Max Roth's book, The Evolution of Cooperation. And we know that during the trench warfare in the First World War, they saw some local forms of restraint, which sometimes emerge between opposing units. So this was called the live and let live system, and can be thought for example, as an example of cooperation. So this kind of live and let live. So the two opposite fronts didn't shoot each other for some longer periods. But why? Why do we see cooperation in this kind of system or in this particular example? For example, here we should say that this was not based on friendship or moral agreement between the two factions, but was probably due to some repeated local interactions who made this retaliation possible. So in general, this is, of course, a challenging problem, but an interesting one. And our idea, I should have said it before, but of course I'm a physicist. So this will be a physicist's perspective on this topic. I know that in your community, there are also, for example, mathematicians or biologists. So I will be really happy to discuss with them later and to know what's their opinion on this topic. So, of course, there are many other examples of cooperation, of these kind of examples. There are many dissemination books which are really good at explaining it. For example, The Evolution of Cooperation by Robert Axelrod, or for example, The Selfish Gene by Richard Dawkins are two, really great books that, I recommend to everyone. So let's start with game theory. So why game theory is important for the problem of cooperation? Because game theory seeks to answer a fundamental question, which is the following. So what should a rational player do in a given strategic setting, and what outcomes are likely to emerge when all players act according to their own interest? And one example, the most famous example probably, comes from an ideal problem, which is called the prisoner's dilemma. And the prisoner's dilemma is basically the following. So we can picture it in this way. So we have two suspects who are arrested for a crime. They are placed in separate rooms and offer the same deal. They can betray the other. So the strategy here is to defect, is defection, and go free, while the other will get a harsh sentence. Or the alternative, cooperation, is to remain silent and receive a lighter punishment if the other does too. But of course, if they both betray each other, they both receive tough sentences. So from a game theoretic perspective, we can try to reframe this phrase in a mathematical scenario and introduce what is called the payoff matrix. So we have a player A, a player B, and each of them has two different possibilities, two different strategies. We could be cooperation, so to cooperate with the other, as I said, to remain silent, or defection, so to betray the other and go free without saying that they were so without saying anything to the other. And of course, here the payoffs are an example, but we can picture it this way. For example, we have here that both cooperation could give three let's think about for example a numerical value to be a reward for both of them. So if they cooperate, they both gain 3 as a value, and this, I mean, looking at it, could be the best option for both of them. But we see that, of course, if we know that the other is going to cooperate, we could try to defect and we will gain a 5 as a reward, and the other will gain 0. And symmetrically, it is the following. So if I choose to cooperate and the other defects, I will get 0, and the other will get 5. And of course, if we both defect, we will get a 1-1 reward for both of them. So, I mean, the prisoner dilemma is one of the main examples for these kind of scenarios. We can picture it in this way, and of course, this is a really important, example for many real social dilemmas, many real world systems. For example, for pollution, the overuse of common resources, academic competition, public good games, and so on. So this could be the starting point of our talk. And of course, this is not the only game that we can think about. So this one was really interesting, but there are other games. For example, I know that everyone knows the rock, paper, scissors game. So this in the payoff matrix could be represented in this way. So just the first line to see if we got used to this notation. If we both choose rock, we got a tie, so no one gains anything. If I go for the rock and the other player goes for paper, I lose, so I get -1, and the other gains 1 as a reward. But if I get rock and the other gets scissors, I gain 1, and he gains -1. So this is the payoff matrix for the 3 strategies. So of course, this is not about cooperation in general, but just to show that this is a powerful scenario to, picture many different real-world scenarios where, for example, this could be an alternative. And I will discuss later why, for example, rock, paper, scissors is an important game for a biological perspective. I will now explain other 2 games, which will be the core and really important for my work later. So I will try to spend some words about them. And the first one is the snowdrift game. So in the snowdrift game, basically, there are 2 possible strategies, of course, again, to cooperate or to defect, and we can picture it in this way. So there is a snow on the street, so the 2 cars, which are coming one from the other way and one from the other, cannot pass. They have to go down from the car and try to shovel the snow. Of course, if they share the cost, both get through. So they could both choose to cooperate, so to shovel, and they both will gain 3 as a reward. But for example, one could choose to stay in the car, so free ride the other, and let the other do all the work. So let the other person shovel all the snow pile which is on the street. And in this scenario, of course, there is not a cost implied, because one of the one who's defecting is not shoveling anything, so doesn't have to pay a cost, doesn't have to pay any fatigue to do the work. So we gain more than cooperating, so 4, and the other will gain 2 because he has to do all the work for the other. And of course, this is symmetric, but of course, if they both choose to defect, the result would be 0-0, of course, because they cannot pass, so there will be no reward for none of them. And another important example is the following, is the stag hunt. And stag hunt can be pictured in this way. So the two players could choose to cooperate. So maybe try to hunt a bigger animal, for example, a stag. And of course, the bigger animal will give a bigger value. So they high reward, I would say. So if they both choose to cooperate and go to hunt the stag, they will both gain 4 as a reward. For example, of course, these are just numerical examples. But on the other way, if they decide to defect, one could go to hunt a hare. But in this scenario, of course, the one hunting a hare will gain 3 because it's enough to be alone to catch the hare, but it is not enough for the other player to catch the stag. They must be in two people to catch the stag. So one will gain 3, and the other who was cooperating and going for the stag will gain 0 because alone cannot catch the stag. And so this is another specific, scenario of a particular game. And the last 2 games, so the stag hunt and the snowdrift, with the prisoner dilemma are an important class in game theory, which are called social dilemmas. So the social dilemma arises when the individual incentives lead to collectively suboptimal outcomes compared with mutual cooperation. As we saw before, mutual cooperation is better, for example, in the stag hunt or the prisoner's dilemma, but we know that the unilateral defection could be an interesting alternative for one who is sure that the other is going to cooperate. And to formulate a mathematical description of these social dilemmas to picture in one unique payoff matrix all these examples I did before, so the prisoner's dilemma, the snowdrift game, and the stag hunt, we can think about a matrix who's the following. So we have, as before, 2 possible strategies, C, which stands for cooperation, and D, which stands for defection. And we see that the rewards are the following. Of course, now I'm not picturing the 2 rewards because they are symmetric. So if they both cooperate, they gain 1. If one decides to defect while the other is cooperating, we'll gain 1 plus this dg, and the other will gain minus dr. And if they both choose to defect, they will gain 0. So depending on the values of the dg and the minus dr, which can be thought as an incentive, dg is an incentive to defect against a cooperator, because of course this usually is called temptation, because I have 1 plus something, so I gain some more value if the other is cooperating with respect to cooperating with the other. And minus dr is an incentive to cooperate against a defector. So of course, if the other is defecting, I will gain minus dr. So depending on the values of these dg and dr, we can think about mainly 4 different social dilemmas. So picturing this in a plane, in a dg for the x-axis and dr for the y-axis plane, we have the following scenario. So the upper left quarter is dg positive and dr positive. So we see that the defection against cooperation is higher than 1. So one would think that could be a good idea to defect against the other if the other is cooperating, and the other is minus dr. So again, here dr is positive, so the other will gain a negative reward. So as I said, the prisoner dilemma is a scenario like before, and I know the outcome will be really harsh if both of them decide to defect, because they will both gain 0. And for example, the other one is the stag hunt. As I said before, here the G is negative and the R is positive. We have this snowdrift game. So the cooperation is shoveling and the faction is staying in the car. And here the G is positive while the R is negative. And the last social dilemma, which is not properly a social dilemma, is the harmony game. I'm saying that this is not properly a social dilemma because in the harmony game, we see that the G is negative and the R is positive. So the better strategy for both of the players would be to cooperate. So there is not a real social dilemma behind it, because the best choice is to cooperate with each other. So This is the main framework on which we'll build all the, all the work and all the things I'm going to say later. So far, we had two players who were interacting and they will choose to cooperate or to defect. But we could think that from two players, we could shift not only by a two-player game, but a two-player game played inside the population. And the main idea behind this thing is that, and of course this is called evolutionary game theory, is that then in evolutionary theory, the fitness of a trait or a behavior is usually determined by its success in promoting survival and reproduction. So as Herbert Spencer summarized Darwin's theory, this is called the survival of the fittest. So as I said, this suggests a shift from 2x2 games, so only two players deciding which is the best strategy against the other, to a population perspective where agents and individuals interact with each other and may update their strategies over time. So starting from this, let me give a pictorial example of this population example. So we could think about a population, and of course we have two colors because, for example, red is a defector and green is a cooperator, and we want to see the evolution of the strategies inside the population. And how can we model this evolution of strategies inside this population? The idea could be the following. So we could start by choosing a player, which we will call a focal player. And the focal player will basically be interacting with K other individuals inside the population. So by now, the other individuals chosen are fully random. So I'm choosing randomly the other people with which I'm interacting. So what happens? He interacts with K individuals. Here the focal player is in blue and the other individuals are in light blue. So they will perform 2x2 games, and the focal player will gain a payoff, pi, which is the total payoff due to the interaction with the K individuals with which he is cooperating. So he will gain pi I. But we could think about another player, so a model player, which now is in, I would say, purple. And again, he interacts with other player, pink, represented in pink color. And of course, again, he will gain a total payoff, which is pi g, given the 2x2 interaction with the other. So he's playing with him, and he gains a pi g as a total payoff, as a total reward for his interactions. And so we could think, okay, the focal player has gained a total payoff, which is pi I. The model player has gained a total payoff, which is pi j. So pi I could think, okay, now I'm going to confront with the model player and see if the model player has gained more than me, probably his strategy is better than mine. So to make this, in a more smooth way, the idea is to introduce the Fermi rule, which of course is important for physics because it's basically the Glauber dynamics for spins. I will not talk about this, but of course I can explain it better later. So the main idea is the following. So the probability for the I player, the focal one, to adopt J strategy, the model player, the probability can be written like this. So it's 1/1 plus the exponential of minus beta. Here beta can be think as a selection parameter, so the intensity of selection, so how fast and how important is the payoff difference to choose this update of strategies, or of course beta is an inverse temperature. So from a physicist perspective, this is of course the inverse of the temperature, for example, in a spin model. And pi j and minus pi I are of course the difference between the model player total payoff and the focal player total payoff. And of course, we can picture this probability in a plane where here on the x-axis you're seeing this difference, so pi j minus pi I, and on the y-axis you're seeing the probability of y adopting j strategy. And here the different colors are given by different values of beta. And you see that, of course, as beta becomes bigger, here we see that the probability is quite, divided between deciding to adopt the strategy or to not adopt the strategy. So here is zero, so the difference between the two is zero. Of course, here there are the probability to change the strategy is 50%, but in general, this could be made smoother choosing a proper inverse temperature, a proper intensity of selection. So usually this is how the evolution is done. So we think about a population, we get a focal player, we get a model player, they interact with k individuals, they gain a payoff, and then they can over time decide to update or not their strategy in the population. So let's think about this model inside the social dilemmas that I introduced before. So this was the dilemma plane as introduced before. And of course, we have different outcomes depending on the game that the population is playing. So I said that they are playing 2x2 games with all the individuals in the population. And we see that the outcomes are different actually. So for each one of the class, we have a different equilibrium. Here, rho that I'm picturing is the fraction of cooperator at the equilibrium. So we have a population of, let's say, n individuals, and the fraction of cooperators are, of course, the number of cooperators over the total number of people inside the population. And this is depicted as rho. So we see that in the prisoner dilemma, the equilibrium strategy is full defection. In the Snowdrift game is a mixed one. In the Harmony game is the full cooperation. And the Stagant is the stability. So let's make it clearer. So let's think about an animation to see this. Let's start from the Stagant scenario. So let's just to recap what I said. The Stagant scenario is cooperating or defecting, depending on choosing to hunt for the stag or hunting the hare. And actually, this is what happens. So here on the y-axis, you're saying the fraction of cooperators over time and time on the x-axis. And you see that I'm starting the population with different initial values. So here, for example, is 0.1, 0.2, 0.5, 0.8, 0.9. And these are the initial, this is the initial fraction of cooperators in the population. So as time evolves, we see that the population, depending on the row zero, so depending on how many cooperators were in the population, we see that the population could converge to an equilibrium over here, which is full cooperation, an equilibrium here, which is full defection, and these two are the stable ones. But of course, if they are split equally, so 50% and 50%, they could gain they could reach an unstable equilibrium where they do not update their strategies at the end. So trying to grasp an idea of why this happens. Of course, if there are many cooperators at the beginning, so hunting a hare is, not an intelligent strategy because there are many people going to cooperate. So if many people are cooperating, why not going to catch a stag and gain a better reward? But if the initial fraction of cooperators is low, of course, there are a few people going to catch a stag. So I'm not sure if the other is going to catch a stag with me. So it's better to catch alone and no one is going to cooperate at the end. And of course, we could generalize. So this was the Stagant scenario, which is here. So in the upper left quarter of our plane. Of course, the prisoner dilemma goes to full defection because we don't know what the other is doing, and cooperation has a lower income with respect to defection if the other is cooperating. So everyone in the end defects with each other. We don't see any cooperation emerging in our population. In the harmony game, as I said, this is not a real social dilemma, so everyone is going to cooperate in the end. And in the Snowdrift game, we see actually a stable equilibrium in the middle. So irrespectively of the initial fraction of cooperator rho zero, we see that the population in the end is going to have, we would say, a mixed strategic profile, because, of course, here it's nice to have half of the people which is going to shovel for the snow and half of the people which are not, so they are just staying in the car and waiting for the other. So I hope that I've been clear enough. These are the four expected scenarios for the four fixed game social dilemmas, depending on the point I am choosing in the social dilemma plane. As I said before, of course, these are social dilemmas. This will be the main topic for today's talk, but games are general. So the same behavior, the same update rule could be done for other games. And for example, as I introduced it before, could be the rock, paper, scissors. So we have three strategies, rock, paper, and scissors. And we see that the evolution over time is the following. So there is not a dominant strategy, because if everyone is going to choose rock, the other are going to choose paper to gain a better payoff. And so if everyone shifts to paper, then the other are going to choose scissors. And of course, this is a cyclic behavior, and they will continue to have this behavior. Let me picture it another time. So this is the evolution. So we have different colors, and over time, the frequency is evolving. And of course, in this triangle, we see a cycle between the three strategies. So I would say that this is a powerful scenario, because we can picture a population which is playing a game, and the game could be, I mean, anything, as far as I'm able to write it in a proper way in a payoff matrix. Of course, this was a more, let's say, local update, the Fermi rule that I introduced before, but this could be mapped directly to an analytical approach, which is the replicator dynamics. So the same behavior we see in these simulations where we choose this update of strategies can be mapped in the replicator dynamics, where the equation is the following. So rho, again, is the fraction of cooperators over time. And we see that the derivative over time of the fraction of cooperators is given by the fraction of cooperators, the fraction of defectors, so the two frequencies of cooperators and defectors, and the difference between the two payoff gained by cooperators and defectors. So if we solve this equation, this ODE, with the proper payoffs in delta pi, we gain the same behavior that I showed just now in the animations. So far, I mean, we introduced a new way to map and to describe evolution in a mathematical way, from a mathematical point of view, game theory and then evolutionary game theory. But we could think that this is kind of a made-up example, because, as I said, in the population there are focal and model players which are chosen randomly, but also the people they are interacting with are chosen randomly. But of course, this is not a real-world scenario, because we do not interact randomly with people most of the times. It could happen, but probably we interact with neighbors in our real life. And neighbors could be not just geographical ones, but also, for example, neighbors because we collaborate on the same topic, we do sports together, I don't know, many ideas. So usually it's intelligent to have a shift between random population to networked or structured populations. So to study these evolutionary games on networks. So as I said, in the model introduced before, the population was well mixed in the sense that the interactions were random. Of course, this assumption greatly simplifies the analysis, but it neglects the fact that in most real-world systems, as I said, biological, ecological, social, and so on, the interactions are inherently structured. For example, as I said, animals interact through social networks, scientists collaborate through co-authorship or citation networks, microbes interact locally in spatial colonies or, for example, biofilms, and so on and so forth. So to capture these effects, these evolutionary dynamics, this evolutionary game scenario can be extended and already has been extended to structured populations. What do I mean by a structured population? So as a physicist, of course, this is an assumption. I know that this is maybe strange for who doesn't come from physics, but the main structured population scenario that I could think about is the lattice, of course. So here I'm showing a lattice. So the initial fraction of cooperators are 0.5. And we see that here in yellow, there are the cooperators, and in blue, there are the defectors. They are initialized randomly. So each point is assigned with cooperators or defectors with a completely random, in a completely random way. And we could think about, so now the individuals update the strategy due to the interaction with the neighbors in the networks. So, for example, one person which is here is going to interact no more randomly with people all around the population, but with the, for example, 4 people around him, 8 people around him, 16 people around him. I don't know. You choose, you pick a number and try to do the simulation. And of course, the model player also is coming from the neighbor. They both update their strategy, and afterwards, they both, calculate the payoff, and afterwards, they will try to update their strategy with the rule I introduced before. So let's reproduce the animation. What happens is the following. So this is a prisoner's dilemma. As I told you before, if we play this exact game in a well-mixed population, so where interactions are random, if you remember well, or independently of the starting value of cooperation at the initial point, at the initial time, at the end, the population will arrive to a full defection state. So everyone is defecting in the end. But what we see here, let me reproduce again the animation. What we see here is the following. So we see that the population is not going to full defection, but is keeping a, I would say, quite stable level of cooperation. So the fraction of cooperator is around 0.5, 0.6. And we see something really cool, of course, if you're a physicist, happening in the lattice. So you see that we introduced the population as a random one. So yellow and blue were splitted randomly all over the lattice. But right now you see that there is an emergence of cooperation, not in a, strange, disordered way, but in an ordered way. So here we see that there are clusters of cooperators, which are trying to, of course, stay close to each other, because they know if that the other people who I'm interacting with are cooperators, I'm going to gain a higher reward than if choosing a defector as a neighbor for me. So this is, truly interesting from my perspective, not just because we have found a way to show that, of course, from simple mathematical principles, we see a level of cooperation which is stable, as we see in real-world scenarios, without requiring no particular rules, just the network structure, just a topology inside my population. But of course, from a physicist's perspective, this is really interesting because we observe these kind of plots. So on the x-axis, I'm showing the temptation to defect, so the dg parameter I shown before, and on the y-axis, I'm showing the density of cooperators. And if you're a physicist, you, of course, now have the intuition to say that this is a phase transition. So we see that if the dg is low enough, the population could go to a full cooperative state. And as the temptation to defect, as dg grows, of course, defection is more as a bigger incentive. So we see that we have this phase transition. So as dg grows, we arrive in the end to a non-defective scenario. But with respect to what we said for the well-mixed scenario, here we should have expected a zero value independently of dg. And here we have a way to see an emergence of cooperation just due to the lattice structure. Of course, lattice is, and of course, sorry, just let me finish. About the lattice, of course, this is a phase transition, can be studied from the universality class and all other interesting, aspects for physicists. And of course, in the lattice before, so in the frame that I showed, you can see that there will be a percolation, some percolation effects, and this, of course, can be studied with the tools from disordered systems or from non-equilibrium statistical mechanics. And of course, as a physicist, I have many tools to use to try to answer to this main question of cooperation. But as I said, of course, lattice structure is not the best one, probably, because, of course, we know that we do not interact through lattices. We know that, for example, there exist hubs in social networks, so people who are really central and have many neighbors. Or, for example, we know from the experiment also from 1960, I think, more or less, about the small world property of real world systems. For example, we humans live in a small world network. Of course, this can be studied in other topologies, so not just the lattice, but we could think about these evolutionary games being played, as I said before, so interacting in 2x2 interactions in different topologies. Just as an example, I won't discuss all the outcomes that we see for the other networks, but for example, in the Erdős-Renyi one, we see here again the yellow are the cooperators, the blue are the defectors, and again we see a stable, more chaotic probably, but still a stable level of cooperation in the end. Of course, this stochasticity that we see is due to a finite size population. So, of course, as n grows to infinity, this stochasticity is less and less important and is more close to a single value. So, this is the overview about game theory, evolutionary game theory. Evolutionary game theory on networks, which is, I mean, better, and let us explain better these examples and this problem of cooperation. But this is not enough. So more recently, another framework that was introduced and on which I'm working on, and I will shortly present my recent work about it, is coevolutionary game theory. So why coevolutionary game theory? So in a phrase, a natural and significant extension of this framework is the consideration of coevolutionary dynamics. While so far we have considered the evolution of strategies against a fixed backdrop of interaction rules and population structure, coevolutionary games expand the perspective. Not only strategies evolve, so far in this example I showed before, the only thing that was evolving over time were the strategies. So the strategies over time were evolving. I could choose to change between cooperation or defection or rock, scissors, paper. But now not just the strategies are evolving over time, but also the environment determining the payoff endowments of strategies is evolving. And of course, the coevolution can be thought in many different ways. For example, we could think that we see a coevolution of the network structure. So for example, if I am not happy with the people I'm interacting with, I could decide to cut the link with these people and find new peers, find new people to interact. Of course, the payoff metrics could change, and we will discuss this in a bit. And of course, we could see also the coevolution of personal traits. So we could introduce different variables, for example, age, teaching activity, and so on and so forth. And we could try to see the evolution of these aspects inside this coevolutionary framework. Just to give an example, I could think about reputation. So reputation is one of the mechanisms that I could introduce. Of course, if I interact with people and I choose to cooperate, my reputation increases, so the value of my personal reputation increases. And if I defect, the value of my reputation decreases. So due to this reputation mechanism, I could change my Fermi rule that I showed before. So now I'm not choosing randomly the people I'm interacting with, but maybe I'm choosing the people who has a higher reputation than the others. And of course, this is one of the main coevolutionary mechanism that could be introduced. So this is the idea behind the coevolutionary game theory. I can discuss all these aspects later, but let me focus on my recent work about coevolutionary game theory. And our main idea, of course, this is not a work that I made by myself, but there is a huge group who are working on this thing, is about endogenous feedback. So let me give a brief motivation. We know that in many social, ecological, and economic systems, the incentives are not fixed in advance. They are continuously reshaped by the collective behavior they produce. The level of cooperation and population can modify norms, regulations, market conditions, resource availability, institutional responses, etc., which in turn alter the incentives faced by individuals. So what I'm saying, which are the scenarios that I'm trying to picture with my model. For example, you see that if you're in a city and everyone chooses to cooperate, let's say that in our scenario, cooperation is to move with a green mean of transport, for example, by bike. Uh, of course, if many people choose to go by bike, the government could choose to implement new green areas, for example. So the game changes because more green areas are better for cooperators. So cooperation could be widespread and could emerge way and way. I mean, more than before. So in general, I mean, this is just an example. We could discuss about other example, of course, but this is one of the examples that I'm trying to explain with my model. So the idea behind it is that collective behavior will change the environment in which the game is played, in which the population is updating its strategies. So, two main questions to address. I hope to address them well. What happens when the rules of the game are not fixed, but are reshaped by the population playing it? And if the game changes with the population, what new dynamical outcomes can emerge? So, just a brief recap on what we saw before, because it is important for us to have these ideas really clear in our mind. For example, in the Stagant, we are in the upper left quarter, so here, we see that we have a B-stability. So depending on the fraction of initial cooperators, we see that the population will go to 0 or to 1. So we'll go to full cooperation or to full defection. And in general, for example, in the Snowdrift game, another game, so we're in the lower right, quarter, we see here that irrespectively to the initial fraction of cooperators, the population will converge to a stable mixed level of cooperation in the middle. So again, what happens when cooperation does not only evolve within a game, but also changes the game being played? And as a starting point, as I said, this was the fixed game scenario. So the game, we have cooperation and cooperation, defection and cooperation, cooperation and defection, defection and defection. So this was the fixed game scenario that we studied before, and the G and the R could be chosen as we prefer to explain a different social dynamics. Social dilemma. In general, this was, generalized from a coevolutionary perspective in this way. So principally, the first work was about Weitz, and then it was later generalized also by Tillman. We see that we can think about the game over time, not as a fixed game, but as a, for example, here, a convex combination of two games, G1 and G2. And the convex combination here is weighted by eta of t, and here eta is an external dynamical system. So we could say that, for example, if we have a resource that is decaying over time, for example, the seasonality of the payoffs, we have a tree with many apples. If there are a lot of resources, many apples under the tree, everyone can cooperate because the resources are many, so everyone could share all the apples in the trees. But of course, if this resource decays over time, so that the number of apples reduces over time, of course, cooperation could not be the best idea because there are few resources, so sharing could be not enough for all the people, and of course, this could introduce defection inside the system. So this was already done, as I said, by Weitz and Tillman and all the co-workers in these years. But our perspective is a little bit different because we are interested in studying a game where a collective, I would say, endogenous behavior itself drives the evolution, not an exogenous system. So here, as I said, eta of t is an external and exogenous system, an external dynamical system which has its own external dynamics, but we're interested in a collective behavior of the population. So we want an endogenous variable to join this evolution of the game over time. And our idea, so our endogenous feedback model, it can be pictured in this way. So the game played, again, G over time, is a convex combination of two games, G1 and G2 as before. But here, the function which is choosing which is weighting this convex combination is not an external variable, but is an internal one. Is a function of the fraction of cooperators over time. So the fraction of cooperators over time decide by themselves which is the game which is going to be played by the population later in time. And of course, this f can be generalized in many ways, this function. And here we could also introduce a tau, so a delay inside our model, so that the game does not evolve due to the instantaneous fraction of cooperators, but due to a previous level of cooperation inside the population. So this is the main idea. But to start, please let me be simple. Let me introduce a simple scenario. So let's just consider the linear and instantaneous case. So the game becomes like this. So the game over time is given by a convex combination of two games, G1, G2, and here the convex combination is driven solely by the endogenous parameter, which is the fraction of cooperators over time. And of course, we could picture this in our plane that we introduced before. So we could choose G1 and G2 wherever we want inside the plane. For example, we could think G1 staying in the harmony game and G2 staying in the prisoner dilemma class, in the prisoner dilemma game. And of course, this convex combination is weighted by the fraction of cooperators. So the game moves along the segment which starts from G1 and ends in G2. So let's try to picture it again. We can think about our population. Our population can be started with a different initial fraction of cooperators. And this is what actually happens. So this one was G1, this one was G2, and the dots that you see inside are the fraction of cooperators at the initial time. So here, for example, you see that the fraction of cooperators is 0.1, so the game is shifted on the segment at 0.1. Here is 0.3, 0.5, 0.7, 0.9, etc., 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 etc. So one main thing that we can see is that depending on G1 and G2, the game could be in G1 class, G2 class, but also in a middle class, for example, here the stagnant game, depending on the fraction of cooperators over time. So let's start the population. So we have here the points. So 0.1 is the initial point here. 0.3, the 0.2, sorry, is the other point, 0.5, 0.7. And okay, let's see how the population behaves under this game, under this endogenous feedback scenario. And what we see is the following. So the population, in the end, converges to a stable level of cooperation, as we can see. So over time, irrespectively of the initial condition, everyone arrives to a mixed level of cooperation, which is, in this case, for example, 0.3. But of course, if the population reaches an equilibrium, the fraction of cooperators does not evolve anymore, and therefore also the game does not evolve anymore. And we see here that the game that we can term equilibrium game is here in the stagnant scenario. So the population is effectively playing a stagnant game, but as you can see on the left, this is the stability landscape, the fraction of cooperators over time that we are seeing. And of course, as I said, this is our equilibrium game. So again, we can picture a population. We see the fraction of cooperators evolving, reaching an equilibrium, and also GT is fixed. But if you remember well, now the population has converged to an equilibrium game. And this equilibrium game is in the stagnant region. So, okay, this is the behavior under our endogenous feedback. But what happens if the population is playing that exact game without endogenous feedback? So now the game is fixed and is not evolving. So if we let the population play the same exact game in that point, what we see is the following. So we don't have this stability, but as expected, we see the classical behavior of our stagnant. Depending on the initial fraction of cooperators, we see full cooperation or full defection with an unstable level of cooperation in the middle. So playing the very same equilibrium game that we reach in our endogenous feedback, we see this behavior, this strange behavior. And of course, as I said, let me picture it back. Here, the population converge to a stable level of cooperation, and which is mixed, so it's 0.3. But if we let the population play the very same exact game, this level of cooperation becomes unstable, and the population will go to a full cooperation or full defection state. So these new dynamical regimes that we found, and this one is one of the examples, are what we call chimera games. So what are chimera games? They are hybrid states in which the population reaches a stable cooperation level, which appears inconsistent with the dilemma class of the game being played. So they reach an equilibrium game, which is in the stagnant region, but if we just see the population playing that specific game, we should expect a completely different behavior. So we have a kind of, we see that this kind of, that this endogenous feedback is kind of reshaping the stability landscape. So what before was stable, was unstable, now becomes stable. And of course, the same is for the other scenario. So what before was stable now becomes unstable, just by introducing this simple endogenous feedback with a linear and instantaneous shape. So just to picture it, to frame it a little bit better, this is what happened with when the game was fixed. So this is the game being played. The population can be started with cooperators green and defectors red, and depending on the fraction of cooperators over time, we see that the two possible outcomes could be full cooperation or full defection. But accordingly, here, we see that in our endogenous feedback game, the population converges to an equilibrium game, but now these two scenarios converge to a mixed stable equilibrium, which does not evolve over time. So we have this kind of different stability landscape only due to our endogenous feedback. Of course, in general, this can be studied in different ways. As I said before, this was the linear case, and the linear case can be figured not in an instantaneous way, but as a delayed way. So this tau becomes a delay parameter. So now the game does not depend on the actual level of cooperation, on the present level of cooperation in the population, but depends on a previous and a past level of cooperation inside the system. And as tau grows, we see some technical things. We see a hop bifurcation depending on the value of tau, but just with an animation, what we see is the following. So here I'm depicting different values of tau, and we observe that here this chimera mechanism still, is here because this is the stable equilibrium, and due to the delay, the game, and so the fraction of cooperators, is oscillating around our chimera game that we found before. So chimera games are, still persist also in the delayed scenario, but we see these sustained cycles around the chimera game if tau big enough is introduced. And of course, as I said, this could be generalized to networks. So let's see the behavior of our endogenous feedback model in a lattice. We see the evolution. Again, we see cooperative clusters forming. The level of cooperation is stable, and the population is still playing a stagnant game, where, as I said before, usually we would expect full cooperation or full defection. So this is kind of an original and really strange behavior that it's happening only due to the endogenous feedback system. And of course, this was a lattice perspective. So as I said, chimera games persist also in these network scenarios, but this could be thought in different other scenarios, for example, in a Erdős-Rényi model, and this is what happens. Here the network is difficult, so I'm not sure that you're able to see very well, but here again, the game is oscillating around the chimera game, and the population is updating also in the network scenario. So these chimera games seem to persist also in network scenarios. So to conclude, just some take-home messages. This endogenous feedback changes the stability landscape. So when the payoff structure depends on the population state, new dynamical regimes, which we term chimera games, can emerge that are absent in fixed game evolutionary dynamics. And now, of course, the population behavior no longer uniquely reveals the game being played. So we could think that just seeing the behavior of the population, we could infer the game that the population is playing. But of course, if there is an endogenous feedback, we see this reversibility, this new stability landscape. So I don't know if the population is playing a Stagant with an endogenous feedback or a snowdrift without endogenous feedback or a mixed scenario. So, for example, for policymakers, this is not easy because if I want to build an incentive for my population, I could try to infer the game they are playing by their behavior. So I could introduce an incentive, but this incentive could break down completely my expectations because there is an endogenous feedback behind it, which is occurring. And of course, this feedback can become a new mechanism for cooperation in general. So just let me briefly thank all the cooperators, of course, my two PhD supervisors, my other colleagues, Dario, which is a master student who is working a lot on these chimera games, and of course in the network scenario. So all the part on the network scenario is mainly due to his work. So I really have to thank him, and of course the other colleagues. Here are our institutions, and this is a cool QR code where you can see a preprint of our work, which is under review right now, and we hope to have it published very soon. So thank you very much.